Welcome back. I'm so pumped you're joining us for this explainer, because today we are looking at a massive, incredibly thrilling architectural shift happening right now in the world of big data storage. We are exploring the evolution of data file formats, and we're going to view it all through the lens of the datatism T6 technology framework. You see, for over a decade, we've thought of data files as, well, passive buckets. You put data in, you take data out. But that era, it's ending. We're entering an entirely new age where data itself becomes computational. So, let's dive right in.
Here's our roadmap for today. 1. The Parquet bottleneck. 2. Meet the challengers. 3. Passive to computational data. And 4. The post-Parquet future. Part 1. The Parquet bottleneck. Why the reigning champ is stumbling. Apache Parquet has completely dominated the Hadoop and S3 era for a decade now. It is literally the universal language of analytical storage. But despite that massive success, it's hitting a serious wall today. See, it was brilliant for the assumptions of the early 2010s, back when we had slower networks and those narrow human-generated workloads. But consider our modern realities. Today's machine learning pipelines use ultra-wide tables with over 10,000 columns. We've got multi-terabyte per second memory bandwidth and highly parallel GPU pipelines. Parquet's aging architecture simply wasn't designed for this kind of AI-driven, high-bandwidth environment.
To really understand why, let's peek under the hood at this outdated pipeline. When an engine queries Parquet, it usually has to read a massive 1 megabyte data page, fully decompress that incredibly heavy page into heap memory, and only then can it actually execute the query. Think about modern NVMe drives on 100 gigabit per second networks. They are lightning fast. But in this old pipeline, they're forced to just wait around idling because the CPU is bottlenecked trying to decompress all that data. The storage hardware ends up being severely underutilized.
Part 2. Meet the challengers. 4 next-gen formats entering the ring.
Because of that massive CPU bottleneck, we now have a whole new generation of highly specialized formats racing to solve the problem. First up is Meta Nimble, the wide table specialist. Originally developed at Meta, Nimble gracefully solves a very specific nightmare, which is metadata parsing in massive, sparse machine learning pipelines. Legacy formats use these heavy serialization protocols that just choke when you hit thousands of columns. Nimble replaces all of that with flat buffers, which drastically reduces metadata parsing time. We're talking sometimes by over 10x. It is tailor-made for those ultra-wide, 10,000 plus column ML feature tables. Next up, let's meet CWI Fastlanes, the hardware speed demon. Developed by researchers at CWI, Fastlanes has a singular, laser-focused philosophy. Arrange the compressed data so modern CPUs and GPUs can consume it with maximum parallelism. It replaces monolithic compression with a brilliant bit-interleaved transposed layout, all operating across a virtual 1024-bit SIMD lane framework. I know that sounds complex, but essentially it's just a way to process massive amounts of data points simultaneously. It perfectly aligns with how modern hardware natively wants to read data.
So what is the actual result of that perfect hardware alignment? Try over 100 billion. Fastlanes can decode over 100 billion integers per second using compiler auto-vectorization. That is more than 40 values per CPU clock cycle. It makes decompression practically zero cost relative to memory bus speed. It is an absolute game changer for high-throughput scanning.
Let's move right along to our third challenger and see a totally different kind of solution. Meet LFAI Vortex, the extensible Swiss Army knife. Donated to the Linux Foundation by SpiralDB, Vortex is often described as the LLVM for file formats. Just like a compiler framework, it's not a rigid box. It's a highly adaptable toolkit that lets you compose data types, encodings, and layouts dynamically. It basically treats compression not as a passive storage mechanism, but as an active part of the execution model.
And because Vortex lets query engines operate directly on compressed representations, the performance leaps are just staggering. For instance, Vortex can execute random row reads up to 100 times faster than Parquet. By completely bypassing those massive 1 megabyte page decompression overheads we talked about earlier, it can grab individual scalar values with absolutely blistering speed.
Finally, we have the academic powerhouse of the group, CMU Tingwa F3, or as I like to call it, the future-proof time traveler. One of the biggest problems with rolling out new formats is that query engines have to be constantly updated to read them, right? F3 solves this by embedding WebAssembly or WASM bytecode decoders directly into the file's metadata. Think of it like a document that literally carries a safe, sandbox interpreter for its own specialized vocabulary. The files are self-decoding, making them completely immune to future obsolescence. Looking at the whole battlefield side by side really puts it in perspective. Every single one of these formats tackles a specific legacy limitation. You've got Parquet prioritizing disk density but failing to compute on encoded data. You've got Nimble conquering those wide ML tables. Fastlanes targets pure hardware SIMD speed. Vortex delivers rapid scans and computes directly on compressed data. And F3 provides future-proof extensibility. They are all attacking that CPU bottleneck, but from entirely different angles.
Part 3. Passive to computational data. The datatism T6 technology paradigm shift.
Okay, let's zoom out for a second, because here is the real aha moment of this explainer. The crucial point is this. This race, it's not just about finding better compression algorithms. It is a fundamental convergence of passive data state and active computational logic. We're seeing hardware-aware memory layouts that talk directly to the CPU. We're seeing execution happening right on the compressed data itself, bypassing all those intermediate steps. And we're seeing embedded, self-decoding bytecodes. The traditional boundary that used to separate the active query engine from the passive file container is collapsing entirely. Which brings us to this massive, mind-bending realization. The file itself is becoming an executable data structure. Just let that sink in for a moment. Data is no longer just a passive bucket waiting on a hard drive to be opened and parsed. It's actually becoming an autonomous, active participant in its own execution. This is a truly monumental shift in how we architect systems.
Part 4. The post-Parquet future. An M. Night Shyamalan convergence twist.
So, you might be wondering, which of these 4 formats is going to finally kill Parquet and take the crown? Well, here is your M. Night Shyamalan convergence twist. This is not a winner-takes-all deathmatch. Parquet's greatest strength isn't actually performance, it's universality. It's not going anywhere tomorrow. Instead, the strategic timeline shows a phased evolution. In 2026 and 2027, we'll see a dual-format hybrid model. You'll use Parquet for cold archival storage and pass it to formats like Vortex for rapid, active analytics. By 2028 and 2029, the industry is going to standardize around compute on compressed data primitives. And looking to 2030 and beyond, as our hardware becomes even more varied, we'll fully transition to heterogeneous, self-decoding computational binaries.
In this converged future, you as the user won't have to pick just one format. We're going to rely on execution abstraction layers, think something like DuckDB, to act as an intelligent traffic cop. The engine will dynamically route you to the absolute best physical representation for the specific job. It'll use Parquet for cold external exchange, it'll pass to Vortex for active analytics, it'll switch over to Fastlanes for compute-heavy integers, rely on Nimble for those ultra-wide machine learning feature cables, and then use F3 when you need durable, decades-long archival records. The future isn't one single format. It's a completely format-aware architecture.
I absolutely love this quote from our source material that sums it all up. Parquet is the current universal language of analytical storage. These projects are designing the computational language that comes after it. It just perfectly encapsulates this transition from the static storage of the 2010s to the dynamic, hardware-aligned computational formats of the 2020s.
As we wrap up this explainer, I want to leave you with a pretty provocative thought. If your data carries its own instructions, perfectly aligns with the hardware reading it, and can actually decode and compute itself on the fly, is it still just a file? Think about that as you continue your learning journey today. I highly encourage you to explore the datatism T6 framework further to see exactly how this impacts your own data systems. Keep learning, keep questioning, and I will see you in the next explainer.